Recording in progress.
Yeah, now I can see it.
Okay, can you all see the screen? All good?
Yep, very good.
Fantastic. Let's start. Man, Krishna, you kept me very late. Almost 19th of July here. Thanks for your kind introduction, Krishna, and for the invitation to present this webinar. I'm really pleased to be here today with you guys. So I'm going to talk about PFAS, geosynthetics, environment protection, and talk about obviously the concerns and opportunities, because they always come together with the concerns since we try to address some of these problems. So why geosynthetics? Because geosynthetics over the past few decades have become the solution of choice for waste containment systems. And certainly their use has transformed the way we approach the design of this type of infrastructure nowadays. However, at the same time, this has also brought new challenges as they are increasingly used in more challenging environment, very often exposing them to conditions they have not been exposed to before, like in mining, for example. The interaction with PFAS is a very good example of the situation. So what I would like to do today is to share a bit of my knowledge on how we can go about addressing the PFAS challenge. Now, the authorities in various parts of the world were warned about the issue of PFAS exposure a long time back, but they were very slow to react to it. What accelerated their action or their reaction was the fact that the issue made the news. So when the PFAS issue started to make headlines of major news outlets in various countries, this of course increased the awareness of the general public. Once you have books and movies made on the issue, the authorities have no other choice than to react. And that's what has occurred. If you go back in history a little bit, a few years back, the awareness made a lot of authorities react to the issue. And we have seen that in various countries, certainly in the US, at much larger scale than what we have here. Now, PFAS are not kind of new products. They have been developed in the 30s, actually accidentally. There's a very nice book on how PFAS came about in the 30s. So they are factory made chemicals extensively used in industry and consumer products worldwide since the 50s. So although they were invented in the 30s, they really saw a spread of use in the 50s. They were first detected in factory workers in the US in the 70s, and that's mostly at places like the DuPont and the likes, and the 3Ms, I think, as well. The first warning here in Australia came in the 80s for the Australian Defence Force in relation to their air bases, but no really action took place. And if you keep moving along the timeline, in the 90s, that's where we started to detect PFAS in general population. So cases were started to be reported, and certainly the past 2 decades, that's when we started to detect them in environmental samples. And if you want more details on this, if you can go to the website of the ITRC, it's pretty well documented, and they give a good timeline and actually the pretty good history of PFAS. Now, currently we have about close to 5,000 compounds that have been identified. And I recall 2 years ago, there were only 3,000. The reason why we now have 5,000 is simply because the equipment, the analytics, now developed quite well. So they are more accurate. We are able to detect more. Now, why they have been used so extensively is because they have this property that you need, and that allows you to reduce surface tension. So that's the reason why they are used in non-stick cookware, strain-resistant carpets and textiles. They're used as water repellent in clothing. The Gore-Tex is a very good example of that. In cosmetics, and you'll see in a few minutes the range of cosmetics where PFAS exists, and also in a large proportion in firefighting foams, and that's where the issue actually popped up. Now, this PFAS chemical is commonly added as a barrier to food packaging because it resists water, oil, grease, and it makes food more portable. So your pizza box, your fries pack, your noodles pack, they actually, the reason why you don't see grease coming from the base is because it has a layer which is hydrophobic. Yeah, so it is oleophobic actually. It repels grease and oil. So a study which has appeared in 2017, Scheider and all, summarized all this quite nicely by looking at, actually by analyzing some of these packages. Now, what you see on the left side here of my screen, actually here, is a summary of the different materials used where fluorine was detected. So don't confuse fluorine with fluoride. They are two different things. So if you look at, for example, bread wrappers, 56% of these wrappers contain fluorine. The sandwich and burger wrappers, same, but 38%. Paperboard, about 20%. 0% in paper cups. That's good news. At the same time, a study which came about 2 years after that, and last year actually, indicated that women exposed to chemicals commonly used in takeaway containers, like the one we have just discussed, might lead to some health issues. And a very recent study, which came about just a few weeks back, and it came from a study carried at the University of Notre Dame in the US, and they looked at cosmetics. And very surprisingly, they found that high level of fluorine in 50% of these products, with probably the biggest one is the waterproof mascara, which contained about 82% of fluorine. I had to educate myself with all this product. I had to ask my wife to explain to me what is waterproof mascara, and she did explain to me. So it's something that was not known probably 15 years ago, but we are getting more and more information. So we are still educating ourselves, not only with identifying these compounds, but also getting to know their potential effect. So why should we be concerned by PFAS exposure? Well, they are pervasive. They can spread widely. They are persistent, and they can bioaccumulate. And of course, they can have adverse health effects, as it has been reported on several occasions. On top of that, we don't know much about them. Now we just started to scratch the tip of the problem. It's work in progress. But as we move on, we find out more and more about it, and we can obviously take some actions on top of that. So there's scarcity of information in literature, especially when it comes to liners, for example. And with that, there is certainly a very incomplete regulatory structure when it comes, again, to liners. So there's a bit of work now, which started about probably 2 years ago. So the expectation is probably to see more results coming out in the next few years. So I'll be using a lot of acronyms in this presentation, and I did ask Krishna. I sent him 2 papers where everything is detailed in those 2 papers, and the acronyms are obviously explained. So you can either I can send you the papers, or ask. I'm not sure if Krishna has sent them to you already, but they are available, and you can certainly refer to them.
I will post them in the chat box.
Yeah.
So everybody can have access to it.
Yeah, so the most frequently PFAS detected in leachate, and I'll be focusing, of course, on landfills in this lecture, are the PFAS, and they are referred to as the perfluoroalkyl acids. In particular, the PFCAs and the PFSAs. These tend to come back very often when we analyze our leachate. Now, these PFASs are categorized into long chain type, long carbon chain type of PFAS. Typically, of these long chains are PFCAs containing 7 or more carbons, for example, such as PFOA, which is the perfluorooctanoic acid. That's very it's probably one of the compounds that has been investigated extensively. For PFSAs, they are classified as long chain if they have 6 or more carbons, and typical of these type of PFASs are PFOS, the perfluorooctane sulfonic acid. Again, these 2 are extensively investigated, not only from the remediation processes either in the groundwater or soil, but also when you look at landfill leachate. Now, the short chain PFAS for both PFCAs and PFSAs are now referred to PFAS with less than 7 carbon in case of PFCAs and 6 carbon in the case of PFSAs. And it's very important to distinguish between the 2, and you'll see this importance very shortly. More recently, some work has shown that we have what we call ultra short chain PFAS. Haven't heard of them before, but they do exist. And these type of PFASs contain between 2 and 4 carbon links. So they are they do exist, and of course they have a different impact. The reason why we distinguish between the 2 is because of their mobility. So you will see the importance of actually identifying them, because they do have an impact on the way that they will migrate. Now, if you look at the structure of PFAS, and that's in general, so it's combined. Now, it's made of these listed here. This is where you have the carbon and fluorine connections or bonds, and the head is pretty much it's a functional head. So it's hydrophilic. So if you look at, if you try to define it very quickly through this relationship here, this is what defines the length of the structure. Therefore, the tail of the of the PFAS structure, and the R value here is the functional group head. So it's the group head is water repellent. It's not water repellent. It's hydrophilic. It is non-ionic head, and it is pretty much strong to weak acid. Now the tail, it's a different story. The tail has very strong bonds because of these CF bonds. It's very stable, and the longer it is, the more stable it is. It's hydrophobic and oleophobic, which complicates the problem further, and it is heat resistant. Actually, the remediation process in place where they use thermal approaches to get rid of PFAS, they have to use temperatures in the 1,000-degree plus. So 1,000 degrees C is about 1,800 Fahrenheit. So that's the type of temperature you need to actually destructure the molecules. And currently there are some processes available, like Veolia, for example, has a mobile unit where it can cook these contaminated materials. And of course, they can have very long CF chain. And as I said earlier, the longer it is, the stronger the bonds and the more problematic the problem becomes. Now, the major sources of PFAS in waste or in landfills come from various sources. Certainly, PFAS substances have been detected in landfill leachate. It's pretty well documented now. And the source is mostly from PFAS impacted industrial waste, waste from site mitigation. Unfortunately, in the past, they dumped them in landfills, but currently it's not allowed anymore, at least in Australia. PFAS bearing consumer and household waste, which have reached, of course, their end of functional life. Landfill fires is also a source because they used foam, not the firefighting foam. And then any other industrial, commercial, or consumer products landfilled since the 60s, 70s. So these substances in landfill leachate are pretty much very well documented currently. And much of this information, at least in Australia, is now incorporated in geochemical indices for monitoring and planning purposes. Now, to give you an example on the waste stream we have here, this is based on a very recent study we published late last year. Municipal solid waste represent about 14 megaton of waste roughly across the nation. And if you look at it very carefully, if you try to define or at least identify the different components related to their applications, you can certainly distinguish between the cosmetic type of application versus food processing and so forth. And they all have or contain PFAS products. By far, probably the largest will be the construction and demolition type of waste stream, mostly because the contaminated material from the different firefighting facilities, airports, and so forth will have found their way towards landfills. Another category where we have identified quite a lot of PFAS compounds comes from commercial and industrial waste. And again, it's quite a large proportion going into landfills. So when it comes to leachate, so what you see here is kind of a summary of what has been reported in literature. And I deliberately concentrated on 6 type of PFAS, 6 PFAS compounds. They are divided into short chain and long chain. So the short chain are given a star or 2 stars. The other one are long chain PFASs. And the reason why I selected only 6 is because we have plenty of data for these 6, and I will keep using these 6 compounds throughout the presentation. So what you see here is the different concentrations at different places, right? But one thing that you should pick up very quickly is the fact that the short chain PFAS tend to dominate over the long carbon chain PFAS. Most of the landfill you see here, leachate you see here in this table. The exception is China. So if you look at the concentrations here, they are quite different from the rest. They are on the very high end when it comes to concentration. And that's because of the very high loading of long chain PFAS, which was present initially in the West, most likely as a result of their extensive use in manufacturing processes. But in general, the trend we observe in this table stems from the fact that first, PFAS manufacturers started to phase out the production of the long carbon chain PFAS once they were added to the list of regulatory substances. So they become POPs, therefore they become content of emerging concerns. So what happened after that, of course, these manufacturers replaced them with short carbon chain PFAS. However, this shift has led to the use of much larger quantities of short carbon chain PFAS to obtain similar performance than to long chain PFAS. The second reason is that the short carbon chain PFAS are more hydrophilic, therefore they are water soluble than compared to long carbon chain PFAS. Therefore, they tend to be more mobile and can be released easily from the waste. And the third reason is the presence of this short carbon chain PFAS can be actually the result of the degradation of the long carbon chain PFAS and also other precursors. Of course, these numbers are function of landfill age. So that's important to keep in mind. Now, since we are talking about landfill age, the table here is of the same type, but it gives you an indication about what we have actually identified in what we call historic landfills or from legacy sites, basically. And again, if you look at the values provided here based on these references, you can see that the long chain PFAS tend to actually prevail. So they are at higher concentration compared to the short carbon chain. And that's expected because of past practice. You compare that to the current ones, the modern landfills, if I might say so, it's actually the reverse. The concentration of this short carbon chain are actually much higher than the long carbon chain type. So this is what you tend to actually see when you are looking at landfill leachate. It really depends on whether the landfill is very old landfill or a recent landfill. And of course, the presence of a liner will certainly make a difference at the end of the day if we are looking at possible contamination of groundwater. Now, we also have actually leachate from other sources. Typically, when we remove contaminated material from these fire training facilities or airport bases or civil airports, we cannot dump them in landfills, at least based on the new guidelines. Typically, an on-site repository is constructed which means that they have to design a cell within the site where the soil is going to be excavated and store it there until a remediation process is put in place. So very often it is a temporary in-site repository. That temporary can last, of course, few years. So typical of this now, if you look at the concentration here, the long chain ones are extremely high. And that's because in all these sites, they have used the AFFF, the aqueous film forming forms, quite a lot of use, because when you're in fire training facility, what do? You train yourself to put the fire down or out, and you use the AFFFs for that purpose. Now, all these forms contain mostly PFAS, very high concentration PFAS, and quantities of PFOA. Now, why you have a large PFAS being a large fraction of PFAS? It's about 78% of these AFFFs, at least on the old ones. There's also another component which is quite common in these film forming forms. That's the PFHXS, which stands for perfluorohexane sulfonate. Also, you have some other compounds certainly in the mix. So when you compare these two, they are if you compare leachate from these facilities to landfill leachate, there's very big difference. And when you collapse all this together, you can see how different they can be. So it becomes quite clear that you cannot have a one-size-fits-all approach to the design of these liner systems for waste containment systems, as the dominance of PFAS compounds and concentration would be different from one site to another, especially from landfills versus if you look at on-site repositories. So here, the takeaway message is very simple. It is essential to differentiate between the design of liner systems, as they'll be, of course, subjected to different exposure conditions. What about the guidelines for liner systems, as their design is highly regulated? Unfortunately, information and guidelines for liner systems accounting for the presence of PFAS substances are currently very scarce, to non-existent. We have a guideline here in Australia, which is mostly for the in-site repositories, but it has been kind of adopted by the local EPAs on a temporary measure until we get the proper guidelines. So they will look at the reason why you have unlined here, which you wouldn't see in any EPA guidelines, is because some of these on-site repositories have not been lined, believe it or not. But that's because I think it's because of the awareness in the first place, and probably some other issues that led them to believe that if you just dig a hole, you can get away with it. You will have single composite liners and double composite liners as well. And of course, that will be dependent on the concentrations that are allowed in the landfill leachate. Now, the reason why you have only PFAS, PFOA, and PFHXS is because PFAS is classified as a persistent organic pollutant. PFOA is not currently classified as a POP, but it's coming. Health authorities here at least consider PFHX being similar to PFAS. So these two were added together when we have to assess any risks. Now, PFOA, although is not classified as a persistent organic pollutant, it is classified as a class 2B carcinogen, and that means that it is possibly carcinogenic, based, of course, on limited evidence. Just for a sense of scale, 1 nanogram per liter represents 1 drop of water in 20 Olympic swimming pools. So you can see how rigid are the guidelines when it comes to PFAS. Of course, that will change from one place to the other. This is what we have here. HEPA is part of what we call the National Environmental Management Practice in relation to PFAS issues. So it came out about 2 years ago. It has been updated last year. Now, how does it compare with the rest of the world? It is shown here. So we are here. If you look at the US and Canada, US is obviously similar to what we have here, but these are federal type of guidelines that will change depending on the state, both in Canada and the US. I know, for example, Canada, British Columbia or Ontario will have different type of guideline, and the same applies to the US. In Europe, there's not much. Most of the data we have available comes from the northern part of Europe. So if you look at the Scandinavian countries, they have a lot of guidelines when it comes to the screening levels in drinking water. And some other countries in Europe do have that as well. But the information across, if you look at worldwide, it is very limited. Only a few places have indication on the screening levels. Now, what's the, just one quick word here. The reason why you have all these differences, at least this wide variation in the guideline levels, it simply reflects the differences in the perception of risk for different countries. And likely, in my viewpoint, also the uncertainty in the scientific approach taken to assess the risks. So what are the implications of what we have discussed so far on liners, on geosynthetic liners in particular? Typical configuration that we will see in this type of containment systems are shown here. Typically for landfills, we tend to see this type of configuration where you have a single composite liner very often used. It can be a GCL or compacted clay, but very often it is a composite liner, single one. For on-site repositories, for example, you will have a double composite liner. And therefore, it's similar to a hazardous type of landfill, although the cells are much smaller. So this is a good example of the second case of non-site repository. This has been completed recently in the western part of the country, and it is a double composite liner, and the cell is to contain contaminated PFAS type of soils. Now, if you go back to these configurations, if you look at the geomembrane, which typically is used very often, most of the guidelines that will refer to HDPE geomembranes, simply because of their excellent chemical resistance and durability. And that comes from the huge number of work done on these membranes in landfill context and other type of applications as well. However, in the context of PFAS containment, and I think there's the need to have a clear distinction between a liner design for on-site repositories and landfills, as the challenge facing them really depends on the PFAS compound chemistry, the level of dominancy of the compounds in the leachate, and of course their concentration. So in other words, you have to distinguish between the dominance of short carbon chain PFAS versus long carbon chain PFAS. Now, when it comes to the migration of contaminants to these geomembranes, if they are devoid of defects, of course, this migration is limited to contaminants that can partition and diffuse into the polymer comprising the geomembrane, whether it is an HDPE or not. And this restricts the type of contaminant to organic compounds only. So in this respect, the potential migration of PFAS through a geomembrane will be a function of the structure of the polymer. So the density of the material, the thickness, the crystallinity, the degree of cross-linking, the polarity will certainly govern that. And these are all product dependent. And on top of that, so you have to add, of course, the concentration of contaminant and their molecular characteristics. Now, I want to take you back to the structure of PFAS, the general structure of PFAS, just again to reemphasize how complex they are. So what we have said earlier, that typically they have very long carbon chain, the tail, and the tail is hydrophobic as well as oleophobic. And the head is hydrophilic or oleophobic. So basically what it means that the tail is inert. It doesn't interact actively with polar or non-polar chemicals, whereas the head group is reactive and interacts strongly with polar groups, specifically water. Now, when it comes to transport of PFAS through polyethylene, since it is the one widely used in these containment systems, it's important to understand the structure of of polyethylene beforehand. So polyethylene is a semi-crystalline polymer. It has both crystalline regions as well as amorphous regions. So the crystalline zone tend to act as the impermeable barrier for the diffusion of contaminants. So you have these stacks of crystallites here, and you have these ties, molecular ties that basically links each crystallite stack to another. So they are quite, and of course the length is laminar size. That's what you see here. So there's no way that you can have a contaminant going through it, but you have these amorphous zones which are present, these voids or micro voids in the structure. And these micro voids or amorphous zones are readily permeable since the polymer chain here is relatively mobile and not densely packed as what you see here. Therefore, the diffusion process in these amorphous zones is relatively high due to this free volume. And of course, it will decrease with increase in the degree of crystallization and cross-linking, which means that, for example, if you look at an LLDPE, which has it has less crystalline, it is less crystalline compared to an HDPE, means that it has more amorphous zones, you will have more diffusion through the LDPE than the HDPE, which tends to be more crystalline. Now, another property that is specific to polyethylene is its non-polarity, since it has no functional polar group capable of hydrogen bonding. Actually, its structure is a little bit boring. There's nothing that makes it really interesting. So polyethylene is known to be less resistant to non-polar organic substances. For example, aromatic hydrocarbons, which tend to readily diffuse through it. In contrast, if you look at now polar molecules, they tend to exhibit lower affinity with polyethylene, and therefore have very low transport rates through it. So at the end, we really need to be mindful of these differences. Chemical difference PFAS between the on-site repository and municipal solid waste. So that's what you have to really be mindful of. And of course, the challenges that a geoenvironmental experience will be function of the level of PFAS concentration and compound dominance. Very often when you look at these problems, we tend to go with, and that's normal, with a very simple approach to the problem. But if you think about it very carefully, when you have these PFAS products, they are not on their own. They will exist, or they are present with other type of contaminants. And that complicates the problem, especially if you have hydrocarbons or you have N-apples in the mix. It complicates the problem much further. Another aspect, I think another component which is very important to keep in mind when we talk about PFAS compounds, that's what we refer to as the critical micelle concentration, or the CMC. So a CMC is defined as the maximum concentration at which surfactant remains freely dissolved in water, therefore not forming a micelle. So like what you see here. So above the CMC, these compounds here will stay, the number will stay constant, while the number of micelles will continue to increase if you have continuous increase of concentrations. So eventually they will get to a point where the surface tension will remain constant, because at that level, the air-water interface is now saturated. And that's important to most of the PFAS compounds that will have a CMC value, which needs to be identified. It is pretty well documented in literature nowadays. So what are the implications when we talk about CMCs? It's important to understand what happens when you are dealing with a value of concentration which is within or close to a CMC value. So if you look at, for example, these micelles in water, water is a polar solvent. Therefore, the hydrophobic tail of PFAS will tend to aggregate together to form the core of the micelles. However, the hydrophilic head will be at the micelle interface in contact with the water molecules. So it will form a sort of a corona, like what you see here. Now, these micelles, this is where they form in water, but they can also form in non-polar organic solvents. And here they become inversed. So we refer to them as inversed micelles, simply because now what we have seen in water is reversed. So the hydrocarbon tails here are exposed to the solvent, while the polar heads points towards the interior here. Of course, they do that to escape the contact with the solvent. Now, these reverse or inverse micelles are able to hold large amount of water in their interior here. And in that way, what happens after that is that a pocket is formed now, which is certainly very suited for the dissolution and transportation of polar solutes through a non-polar solvent. So this change in the micelle aggregation can facilitate the migration of PFAS solutions through the amorphous region of polyethylene structure. So this is really work in progress. Most of what has been done so far with regard to geomembrane is very limited. There's a bit of work which has taken place. It didn't look at the micelles yet, but we have to start somewhere. And that start has taken place already. So what we have as evidence from literature, if you go through literature, you wouldn't find much about transport of PFAS in polyethylene. What is available nowadays currently, or came from the work done on sampling of groundwater and so forth. If you pick up the guideline on sampling, that will not allow the use of glass or Teflon, but they will allow the use of HDPE containers. Now, there were some studies done on that interaction of long chain PFAS with HDPE containers, and it showed that there was irreversible absorption of long chain PFAS to their surfaces. And the same was done actually for short chain. These are very recent results, actually, which came from outside geoenvironmental engineering. So for short chain PFAS, they tend to remain in solution due, of course, to their high solubility. They are hydrophilic and very mobile. And the absorption into HDPE was almost non-existent. But what is very interesting is what actually the Transport Research Board released about 2 years or 3 years ago in their guideline, where they advocate the use of a different type of polyethylene, and that's the high density cross-linked polyethylene referred to as XLPE, to store these firefighting foams. And that's because they have superior stress cracking resistance and pretty good chemical performance. And the reason why they advocated the use of XLPE is because of their observations of failures caused by stress cracking in the existing tanks, which were mostly made of LLDPE and some of them with HDPE. So what we now, if you look at these evidences, it suggests that probably the use of more polar-based geomembranes, especially with on-site repositories, might need to be considered, as they can offer maybe a more robust option to mitigate the migration of PFAS compounds. A more recent work, which came from Canada, from Kerry's team, looked at the diffusion of long chain PFAS through a 0.1 millimeter LLDPE geomembrane, and it gave pretty low diffusion if you compare it to benzene, for example. Benzene is in the 10 minus 12 minus 13 for PFAS and PFOS. It's in the range of minus 17, so it's pretty low diffusion. However, you have to also keep in mind that all the studies done in the past, especially aging studies, where leachate contained or had the presence of surfactant, resulted in reduction of the OITs, both standard and high pressure of these geomembranes. So, and the reason for that is because now the PFAS is at the end of the day is a surfactant, so it's would probably have the same effect once your geomembrane starts to age in that environment. Now I'll move on to GCLs, since they are also extensively used in these containment systems, and they have been used actually here to contain PFAS contaminated soil. So very quickly for the audience, at least for the one who are not very familiar with GCLs, GCL is a composite material. So it is made of bentonite that you see here, geotextile upper lower, and then it is needle punched across to a process to really make it very stable. And now the key component here is the bentonite, is a monovalent component, which has now significant, is a significant constituent of bentonite. It has very large specific surface area. It is capable of both crystalline and bulk swelling. So it is basically the responsible for the desired physical and chemical attribute that make use of bentonite omnipresent in GCLs. Just to give you an indication on why we use bentonite in GCLs. As soon as it is in contact with a liquid, with water, for example, it will start to swell. So if you follow the short video here, you can see water at the bottom, and as it starts to move up, I'm not sure if the video is more, doesn't seem to work. But anyway, so if it starts to hydrate, the bentonite will start to swell. And once it gets to a gel form, it basically gives you that low permeability that you'd be looking for. So what do we know currently when it comes to GCL hydrogen conductivity? So we have certainly an extended wealth of information on GCL chemical compatibility of every type of chemicals you can think of. What we know in relation to organic pollutants, that bentonite has low absorption capacity to these pollutants. And these pollutants, organic pollutants, can affect the bentonite structure. And of course, if they do so, then it affects the hydrogen conductivity. So what we don't know is the compatibility with PFAS substances when they are in aqueous solutions. And we have a project which has been going on for a year, more than a year now, looking into that. And we have now a couple of PhD students who are working on this project. So let me take you through some of the recent work which has been reported on this interaction between GCLs and PFAS. So the study looked at actually using a real landfill leachate. And that's what you see in this table here. So the concentrations, the different compounds were selected. There were more than 20 compounds in that leachate. We selected these 6 just for the sake of not the consistency with the rest of the presentation. And again, if you look at the concentration, it basically fits with what we have discussed earlier. The short chain one tend to dominate compared to the long carbon chain PFASs. And this is very recent landfill leachate. So all these compounds exist as anions due to the low dissociation constant. And that dominance of the mobile one is important to keep in mind, as you will see in a few minutes. Now, the first step when you look at this type of studies is to see how a conventional GCL will react to these contaminants. So the data you see here is actually what you see is hydrogen conductivity versus time. This is pretty much very short-term type of test. The test itself with all the compounds has been going on for at least 2 years now in collaboration with Geofabrics, which is the local GCL manufacturer. So what you see here is variation of hydroconductivity versus time for a conventional GCL, typically used in landfills. And the permeant is that this landfill leachate we have discussed earlier. The design is always based on first exposure. Therefore, what you see here has not been, the GCL has not been prehydrated. It has been exposed to leachate at the start. But what you see here is the GCL, the same one tested with DI water. So this is basically the reference baseline you have here. And this is typical of what you see in the guidelines as well, where they give a value in the range of 2 to 3, 10 minus 11 under 30 kPa surcharge. So here the permeability is relatively low. I mean, it's in the range of 4, 10 minus 11 after around 70 days permeation. But when you look at this low permeability, I think we should not be misled by it and assume that PFAS will be contained. Because when you look at the effluent after this 60 to 70 days, you'd be kind of surprised. So what you see here, this is the original leachate. Therefore, the concentration, what we have seen earlier for the different products or different compounds. So all the short-chained compounds didn't have any issues moving across. So they are very mobile. So the GCL did not contain them actually. It did contain the long carbon chain in this case, but again, this was dependent on the LOR, which is the limit of basically of these tests were done at the commercial lab. Therefore, the level of accuracy of their equipment is very low, so they couldn't detect anything below nanogram per liter, 100 nanograms per liter. Now, in general, basically, PFAS concentration did not reduce much. So I think that's a conclusion we can make. Even though we had these small changes, they can probably be attributed to the presence of hydrophilic functional groups in the PFAS compound, which kind of offered some capacity for absorption into the bentonite compounds. Now let's imagine that you can actually modify this GCL. Here what we have used was activated carbon. It's a good candidate. So you can offer a sorptive material which can hopefully be able to stop these PFAS compounds moving across. And now activated carbon has very large surface area. It's in the order of 800 to 1500 square meter per gram, much higher than bentonite, which ranges in the 400 square meter per grams. And furthermore, its surface area, its surface is non-polar, which basically results in affinity for non-polar organic like hydrophobic pollutants. So this hypothesis has been tested by looking at the interaction between these activated carbon GCLs and landfill leachate containing PFAS. This is what you see here in this diagram. Again, it's hydroconductivity versus time, but this is for at least a year worth of tests. As I said, the testing has been going on for at least 2 years now, if not more. So the initial result we discussed earlier is here for conventional GCL. This is the modified GCL with activated carbon with DI water as permeant. And the one here is with the PFAS leachate. Now the permeability is still in the range of 10 minus 11. This is obviously, as I said, close to a year worth of testing. The addition of activated carbon impacted moderately on the hydrogen conductivity, but it does have an effect on PFAS concentration, as you see here. Again, the same type of diagram we have seen earlier, where we are reporting these concentrations over time. So what we have here is pore volumes of flow instead of time. Again, if you look at here, this is the total PFAS present in the leachate. The effluent contains the short-chained ones. Again, they were not sorbed, but as you keep going, and if you keep the test going, we could see a change around 8 pore volumes, and then it picked up again afterwards. So although the total PFAS dropped from the initial concentration to kind of the limit of reporting the LOR value, it increased again. And this indicates, first of all, the importance of running the test for a long time. But what is important to see is that the total PFAS, which is represented by the black lines there, measured was dominated by the short-chained ones, therefore PFBA and PFBS. And it was not a surprise to us. The two behaved classically relating to exceeding their absorptive capacity. Now, the likelihood that also that some degradation has occurred, or more likely some of these short-chained were attenuated during the initial flow, have of course broken through. Now, if you look at the other compounds, therefore the long carbon chain ones, here the activated carbon GCl appears to provide a very good degree of resistance to the migration of these long carbon chain PFAS. And that's again not surprising, because powder activated carbon is very effective in absorbing long chain PFAS through hydrophobic interactions, and that's what it seems to be the case in this current investigation. But for the short chain, it doesn't seem to be the case, as you see here, you've seen earlier. The absorption capacity is less, most likely because the binding sites in both the bentonite and the activated carbon were not longer available. So that's something that needs to be obviously addressed in the future. But the mobile ones offer quite a challenge to deal with. Some recent work again on soils, this time where we look at the migration of the short-chained versus long-chained. You look at the short-chain, 67% were at 2 meters below ground surface, long chain only 17%. And that's all because of their mobility. The long carbon chain tend to be slow because of their structure, whereas the short chain ones are more mobile because they are more hydrophilic, they are more soluble. Now, what I would like to do very briefly is to move from the base of the containment towards the surface. And the reason why I want to do that is because when we talk about PFAS, we tend to associate PFAS with landfill leachate, with solutes. We have to go well beyond that, because PFAS can also be in the air. Now, if you look at these fluorotetramer alcohols, the F2OAHs, they can also be released from landfills, mostly to the landfill gas. They can partition to the landfill gas, and they have low water solubility. Some studies done at various places around the world have actually indicated that these PFASs are present around landfills. So if you look at some studies from Canada, they indicated about 90% of the total PFAS picked up in landfills, at least in air around landfills. F2OH was present, especially the 8 carbon, the 8.2 F2OH was present in 90% of the PFAS collected there. In Germany, whether it is closed landfill or active landfill, again, very high concentration of TOH, 75 and 92%. In China, in one of the largest landfills in China, in Shanghai, it was about 75%. So why is this very important? Well, because they can be a source of PFAS in the ground. Now, when you look at the migration of PFAS, especially these alcohols in the air, they can be in two modes. They can come from landfills to the landfill gas, but they can also come from the manufacturing plants. So we are not talking about that. So it goes through vapor phase transport process, basically. Once in the air, it takes time, of course, to degrade. Roughly, based on current studies, about 20 days. That's the lifetime. Why is it important? Because these are precursors. Once they degrade in the air, they will form PFAS. So they will deposit on the ground, and the first rain that will come will, of course, will take them further down in the soil and towards the groundwater. And you end up with contamination caused by PFOS or PFAS and so forth. So that's an aspect which is receiving quite a lot of importance, because first of all, in the past, it was difficult to quantify them in the air, but as equipment now, detection equipment monitoring has evolved, we can actually pick them up. And the guidelines are going to change very probably in the next probably few months, where there'll be a requirement to look at F2OH in air, at least around landfills. We are talking about it here, and most likely it will occur in other places. But you can actually design for it. F2OH is semi-volatile or volatile depending on the compounds you are looking at. So you can take the same approach as you take for when you are dealing with VOCs, and you can certainly minimize their possible migration into the air, and therefore reduce the possible contamination caused by PFAS. Now, the type of cover system is important. Obviously, if you have a composite liner, it will certainly minimize the migration of these F2OH in the air. It will reduce certainly the flux. It depends on if you are looking at single covers, if you are looking at compacted clay or GCL, that will perform, probably their performance will be less, simply because you are relying on the fact that they are really wet. They should be wet or hydrated to provide that possible barrier performance or function. Of course, if you are using a single geomembrane with no defect, it will minimize the problem. But the best approach to it is when you have a composite liner, it will certainly bring the flux really down. So that this is a work in progress as well. Just to summarize for GCLs, when you are looking at these soluble type of PFAS versus volatiles, it's important to look at the partitioning. For example, for water-soluble PFAS, if you have liquid to solid partitioning, which is possible at whether you have very wet, fully hydrated GCL or less hydrated GCL, it's something that is in a way desirable, because it will reduce or it will induce retardation or partitioning away from the leachate, in which it is, of course, more mobile. For volatile type of compounds, if you are looking at air-water type of partitioning, it could be here considered as unfavorable, as it provides an alternative route for transmission. The air to solid partitioning, for example, would be desirable because it will retard the movement of in the primary compound or component. So these are, you know, again, this is work in progress. We look at both. Most likely we'll have more to say on this probably in a couple of months, but this is where we are at this point in time. So I would like to conclude by, of course, talking about a few things here. There are a couple of important aspects we need to keep in mind. The evaluation of these, the effectiveness of these liner systems, at least geosynthetic liner systems, currently is very scarce. And the situation is mostly because of the newness of the problem and the lack of information on the PFAS mobility through geosynthetic liners. Second, I think it's important to not lose sight of the importance of distinguishing between liner solutions for on-site repositories and landfills, because the challenges and performance requirements are different. Limitation and suitable or different type of geomembranes and GCLs for this application need actually to be acknowledged. So basically, you don't have one size fits all type of solution. There's certainly a need to gain better understanding of the PFAS complex chemistry. And this can become ever more challenging once we account for the presence of other contaminants present in the leachate mixes. Of course, this in turn will allow a better appreciation of the fate and migration process that will take place through both the geomembrane and the GCL, which currently are posing a significant hurdle to the development of liner system design that will ensure long-term environmental protection against PFAS migration. So this brings me to the end, and I won't finish without, of course, thanking our sponsors. This work presented today was made possible through funding by the Australian Research Council and our industry partners in this project, GeoFabrics, TRI, Australia, Solmax, Sanversa, and FabTech. Thanks again for your for being here. And now, question time. If there are questions, I'm sure there are many questions, and I'll be happy to answer them. Thanks again for your attention.
Thank you. Thank you so much for your excellent presentation, and you have given us very latest information.